Hello everyone, this is Fahad Makbul from the University of Sargodha, and I am going to present distributed scalable shade bat algorithm that has been developed using Apache Spark to solve large-scale global optimization problems. In this article, my co-authors include Saad Razak and Asif Yar from the University of Sargodha and Dr. Hajra Zabin from University of Cologne. Here is the brief overview of the presentation. I will go through each of this item in detail in upcoming slides. So the idea behind this work is that many real-world problems have increased their scale from few decision variables to thousands or even more decision variables. Like for example, in case of knowledge graphs, we can see that DBpedia has almost 2 million entities and 10 million facts. Similarly, Google Knowledge Graph has almost 500 million entities and more than 3.5 billion facts. So with such a large dimensional space, conventional techniques are not suitable to handle these problems. So we need some distributed or parallel techniques to handle these problems. Also, with the advancement of parallel and distributed computing frameworks like Apache Spark and Apache Hadoop, it encourages us to address large-scale problems and develop scalable techniques using these distributed computing frameworks. So in this article, we have proposed a distributed scalable shade bat technique. Basically, it's a hybrid technique that uses exploitation capability of bat algorithm and exploration power of shade algorithm. The bat algorithm, in case of bat algorithm, search is intensified by the local random search walk. While in case of shade algorithm, it uses a parameter adaptation mechanism using history of successful parameter settings. This is one of its first kind that has been tested for 1 million dimensions, and it has been developed using Apache Spark framework, and the code is freely available at the given GitHub link. Global optimization functions are mainly divided into two types: unimodal and multimodal functions. Unimodal are relatively simple with a single optima, while in case of multimodal functions, there may exist multiple global optimas and local optimas. So global optimization problems are further classified as large-scale global optimization problems when number of decision variables increases beyond 1000 dimensions. So with large-scale global optimization, there comes new challenges. Like search space pattern may change. As we can see in Rosenbrock function, it acts as a unimodal function in two-dimensional space, but it acts as a multimodal function when the dimensions increases beyond 3. So with increase in dimension, we may face curse of dimensionality as well. Such space increases exponentially and makes it challenges to find the global optima. So the increase in such space also costs us in terms of computation time. Evolutionary algorithms are the population-based meta heuristics that are commonly used to solve global optimization problems. They iteratively evolve candidate solutions using 3 reproduction operators. So evolutionary algorithms are capable to solve complex problems. This is due to the reason that they can explore multiple regions of the search space simultaneously. Also, they avoid local optima by maintaining diversity of the population. Although these algorithms have shown promising performance in solving lower dimensional problems, but many of them suffer from curse of dimensionality, which means that their performance deteriorates as the dimensionality of the search space increases. BAT algorithm mimics BAT algorithm and shade algorithm are also population-based meta-heuristics. So BAT algorithm mimics echolocation behavior of microbats. Search is intensified by a local random walk. Each bat flies randomly at a certain position with a varying frequency and wavelength. When a bat finds a prey, it changes its frequency, loudness, and pulse emission rate. BAT algorithm calculates its best solution as a centroid of few fittest solutions. In case of shade uses a parameter adaptation mechanism using history of successful parameter settings. It also stores the mean value of control parameters that are crossover rate and scaling factor. These setting guides shade for selection of future control parameter. Shade finds best solution randomly from few fittest solutions. LSCO techniques are basically divided into two categories: cooperative coevolution and non-cooperative coevolution. Both cooperative coevolution and non-cooperative coevolution techniques are used to divide the population across the partitions. In case of cooperative coevolution techniques, a high dimension problem is divided into low dimension subproblems. These subproblems are then evolved separately on partition. Best solution is obtained by concatenating the best solution obtained from each partition. However, in case of non-cooperative coevolution, dimensions of a problem remains intact, while population of the individual is divided among the partition. Best solution is the one that has the highest fitness across all the partitions. Both cooperative coevolution and non-cooperative coevolution techniques may use island model. So island model basically divides a population into subpopulation, and these subpopulations are referred as islands. Each island can execute an algorithm independently. So island model maintains a population diversity and tries to avoid the local optima. Also, it enhances algorithms' global searchability by exploring search space in multiple trajectories. Apache Spark is an open source in-memory cluster computing framework that comprises of one driver node and multiple worker nodes. So Spark API is available in multiple languages, including Python, Scala, Java, and R. Also, Apache Spark can work with multiple data sources, which may include HDFS, Cassandra, and HBase. In case of Apache Spark, RDD is the core of Apache Spark. RDD is basically a distributed collection of immutable data set that is partitioned and divided across multiple partitions of the worker nodes. So RDD distribution among various worker nodes leverages data locality. So when we talk about Apache Spark operations basically can be divided into two categories, that are transformation and actions. A transformation creates a new RDD from existing RDD, while actions aggregates the elements of RDD and return them to the driver program. Transformations are lazy in nature, which means that transformations don't get executed immediately as soon they are called. Spark maintains the record of pending transformations using RDD. When we call an action, then directed acyclic graph is submitted to DAX scheduler, and it further converts to stages of the jobs. There is a very limited literature available on LSU, especially using Apache Spark. SGA is one of the techniques that used Apache Spark for large-scale problems. They conclude that as they increase the number of islands, network communication increases. That results in increased execution time. Shared ILS combined shared with iterative local search strategies. So they experimented using 100 individuals only, and their focus was on better convergence. GL shared also combined shared with the local search operators. The results of GL shared was competitive with shared ILS. It is important to mention that none of the above mentioned algorithms have shown scalability on very large dimensions. So now we start to discuss our proposed methodology, distributed scalable shared bet. So it's a non-cooperative co-evolution based technique that combines the exploitation power of BAT algorithm with exploration capability of shared algorithm. So it has been implemented using Apache Spark and island model. For communication between the partition, mesh topology has been used. So this is the basic architecture of distributed SSB. We start with creating an RDD. After that, for each partition of the RDD, we call map partition function. When map partition is called for the first time, then there is no existing broadcast. Therefore, we skip the first two steps of eliminate weak solutions and add broadcast solutions. So we directly move to the execution of the algorithm. For half of the partitions, we execute shared algorithm, while for the rest, we execute BAT algorithm. We iterate these algorithms according to the migration interval value, which represents the number of times we can iterate an algorithm before issuing a broadcast. After the first migration interval, we save the evolved population on local file system. So as the last step of map partition, we materialize the RDD to return best solution from each partition. So it is important to mention that we calculate best solution for BAT algorithm by calculating centroid from few fittest solution. While for shared algorithm, we randomly choose a solution from a limited pool of fittest solutions as a best solution. After we materialize an RDD, each partition returns its best solution. If stopping criteria is not met, then we broadcast these best solution. For second and subsequent calls to map partitions, we don't retrieve data from RDD. Rather, we retrieve locally stored evolved population. Then we remove the weak solutions and broadcasted best solutions replace these weak solutions. Remaining execution of map partition is same as explained earlier. We have performed experiments using CEC 2013 benchmark suite that comprises fully separable, partially separable, overlapping, and non-separable functions. We have implemented distributed SSB using Scala and Spark, and the experiments have been executed on a 3-node cluster with Dell PowerEdge R815. We have compared our results with GL Shade and Shade ILS. We have performed Friedman statistical rank tests on the results obtained from 25 execution of each configuration against distributed SSB, GL Shade, and Shade ILS using 15 benchmark functions. So the results indicate that distributed SSB has got better rank compared to its counterpart. We have performed experiments to analyze the execution time for 1000 and 2000 dimensions. So results shows that distributed SSB outperformed shared ILS for both dimensions. However, our technique is better for most of the function compared to GL shade. Scalability is the main concern of LSCO problems. Therefore, we have tested behavior of distributed SSB against its counterparts for 50,000 and 1 million dimensions. So we have analyzed the execution time for F2, F3, and F15 functions at 50,000 dimensions. The results indicate that SSP costs less execution time compared to its counterparts. For 1 million dimensions, we have chosen F12 function that is relatively simple function. Distributed SSB successfully converges to a value, but GL shade and shade ILS throws memory exception. This proves the scalability of distributed SSB over its counterparts. We have analyzed the behavior of distributed SSB against varying number of islands. It is observed that by increasing number of islands, execution time decreases significantly for various functions. Also, we have done convergence analysis for varying number of islands. Increasing islands may improve data parallelism. However, it decreases execution time, diversity, and overall fitness value. We have performed extensive experiments to analyze the effect of migration interval for 10 million iterations. Results indicate that distributed SSB has faster convergence at 20,000 migration interval. However, higher migration interval improves the execution time by reducing network overhead. Finally, we conclude that distributed SSB outperforms GL shade and shade ILS in scalability, convergence, and execution time. Also, distributed SSB is first of its kind that has been tested on 1 million dimensions, and it's also freely available on GitHub. In future, we have plans to apply distributed SSB for machine learning parameter optimization problem. Also, we will try to correlate problem size with the number of islands. Thank you.